Jim wants to create a rectangular garden measuring 1,200 square yards. He wants to enclose two parallel sides with metal fencing costing $35 per yard, and the other two sides by wooden fencing costing $28 per yard. What dimensions will minimize the total cost of enclosing this garden, and what is the minimum cost, rounded to the nearest dollar? So our first step is to draw a picture if necessary, and this is a case in which we can draw a picture. We've got a rectangular garden, and two of the sides of the rectangular garden he wants to use metal. So for these two sides, we're using metal. And then for the other two sides, he's using wood. So we'll let wood be represented by the red. Now our goal is to figure out the minimal cost for this garden. So we're going to be coming up with a cost function that we want to find a minimum for. Now the information that's given to us is we're given that the rectangular garden will measure 1,200 square yards. So that's going to be the area of this garden. Well, the area of a rectangle is width times length. So we can label one side the width and the other side the length. So width times length here is going to be 1,200. So knowing that width times length is 1,200, this equation will allow us to relate one variable to another, which will come in handy when we're trying to write our cost function in terms of one variable. Now in trying to come up with a cost function, let's keep in mind that we can think of this as kind of two pieces, because two of the sides are made with metal fencing, which costs $35 per yard, whereas the other two sides is made with wooden that costs $28 per yard. So since the cost for metal and the cost for wood is different, we're going to break the cost of fencing into cost of metal fencing plus the cost of wooden fencing. I'm going to let C represent our cost function, and I need to write this in terms of one variable, so I need to choose either W or L. Doesn't matter which, I'm just going to go with W here. So W is our variable, so we're writing this in terms of the width of the rectangle. So now the cost of metal fencing, well, it is $35 per yard. So we're going to have $35 per yard, so times however many yards of fencing there's going to be. Well, we've got two sides, so we're going to have times 2W, where W is the width. So that'll give us the cost of metal fencing plus the cost of wooden fencing. Well, the wooden fencing is $28 per yard. So $28 times however many yards we're going to have. So that's going to be 2 times the length, since we have two sides made of wood. So 2 times L. Well, instead of writing L, I want to write this in terms of W. So going back to this equation up top, where we have WL equals 1,200, let's solve this for L. So if I solve this for L, I have L is equal to 1,200 divided by W. So now this allows us to express length in terms of W. So in my cost function, instead of writing 2 times L, I'll write it as 2 times 1,200 divided by W. So now I've written my cost function in terms of just W. So now simplifying this, we have 70W plus, then we have 28 times 2 times 1,200. So that's going to be 67,200 divided by W. So there's our cost function. And what we want to do is we want to minimize this cost function. So to find a minimum, we need to find our critical values. So we find those by taking the derivative. So the derivative of this is going to be 70 minus 67,200 W to the negative 2 exponent. So to find that derivative, I thought of our cost function and writing that W in the denominator, thinking of that being in the numerator with a negative 1 exponent. So our derivative then, we can write as 70 minus 67,200 divided by w squared. Now to find our critical values, we're going to set the derivative equal to 0. So we have 70 minus 67,200 over w squared equal to 0. So we have 70 equal to 67,200 divided by w squared. Now I'm going to multiply both sides of this equation by a w squared to get our denominator out of the, or to get our variable out of the denominator. So we have a 70 w squared equal to 67,200. Dividing both sides by 70, we have a w squared equal to 960. Now let's take the square root of both sides, and we have w equal to the square root of 960, which is approximately 30.98. Now technically we could also have a negative 30.98 for the square root, but since we're talking about the width of a rectangular garden, it only makes sense to talk about positive width. Now to verify that this critical value is in fact a minimum, we can look at the second derivative. So taking the second derivative, c double prime, we get a second derivative of 134,400 w to the negative 3. Now if we plug our critical value into our second derivative, so if we plug 30.98 in there, we get approximately a 4.52, which is positive. So since the second derivative is positive, then that does verify that c of 30.98 is in fact a minimum. So having a width of 30.98 yards in this case does give us a width of that minimizes the cost. Now to get the length, keep in mind that we said the length was 1200 divided by w. So plugging that in for the width, so plugging a 30.98 in for width, we get a length of 38.73 rounded to 2 decimal places. So having a length then of 38.73 yards gives us our dimensions. So now we have our width and our length for the dimensions to minimize cost. Now to find out what that minimal cost actually is, we can plug our w into our cost function. So to figure out the minimal cost, we're going to plug 30.98 into our cost function, since our cost function was expressed in terms of w. So here we have 70 times 30.98 plus 67,200 divided by 30.98. So our cost comes out to be approximately 4,338, and that would be the cost rounded to the nearest dollar. So the minimal cost then is $4,338.